Then let's start it. Okay, hello everyone. Good afternoon or good evening or good morning. I see people from around the world join this meeting and this webinar. Welcome to the first webinar of AM Smart, Advanced Manufacturing of Smart Material and Structures. Uh, my name is Mehrshad Mehrpouya. I am Assistant Professor, University of Twente in Netherlands. First session, we have two great speakers. I briefly introduced them. Uh, we have Professor Xiebin Wang from Shandong University. He is going to give us a presentation about additive manufacturing of shape memory alloys, ternary and ITI shape memory alloys. And the second speaker is Elyas Ghafoori. Professor Ghafoori is from University of Hannover, Leibniz University. I hope I pronounced the name well. And also Elyas is going to give us a presentation about, again, smart materials and application of that in constructions. Before we start the session, for the opening of this event, I asked and invited Professor Ian Gibson. Professor Ian Gibson is my colleague at University of Twente. He is a chair of Advanced Manufacturing Group and the Department of Design, Production and Management. And also he is running as a director of Fraunhofer. The complete name is Fraunhofer Innovation Platform at University of Twente. Also, Professor Gibson, you probably know, and he has one of very great books in additive manufacturing, one of the most cited book that me and lots of other colleagues around was using that for teaching 3D printing course. He kindly accepted to be present in the meeting, and we would like to hear from him at the beginning because uh, I think it would be nice to hear from him about the additive manufacturing of the new generation of the materials and the advancement happened in recent year compared to time he started to work on the additive manufacturing when it was still very new, like about 20 years ago, 25 years ago. Yeah. Uh, Prof. Gibson, Ian, uh, please join us and floor is yours.
Well, thank you very much, Mehrshad. Apologies for my croaky voice. I have a little cold at the moment, but I don't think I wanted to miss this webinar, really, because, Mehrshad, you're absolutely right. It's a very important research and development area for additive manufacturing. In fact, my experience goes back even longer, 31 years now. So, in those old days, we called it rapid prototyping. And in those days, we were happy if we found a material that worked. And in some respects, it didn't even have to be that accurate or that strong. It was really just about creating the complex geometries that we are now so familiar with. But it's evolved and developed over those 30 years. We can still see the fundamental methods have not really changed. But certainly one of the major changes is the development of more and more functionality in the materials that we're using. And this webinar really just highlights that factor. That nowadays we're not just talking about the geometry, but we're talking about other aspects of functionality. And this we're referring to as smart materials, or in some respects 4D printing, or whatever we would like to call it. But the key now is that we have a lot more tools to play with. We've got a lot more, many more dimensions to look at, aside from just the geometrical factors. And so adding sensors, adding functionality in terms of movement or variations in the mechanical or other properties, these are very much at the forefront now. And you know, I congratulate you guys for choosing to be studying that. And I really look forward to seeing how what is now what we call additive manufacturing or 3D printing is going to develop.
Yeah, thank you. Very nice word. Without saying any other words, I would like to just start to invite the first speaker, Xiebin Wang. Please share your presentation with us, and you can start. I just say, uh, in general, how's going to be in this meeting and webinar. We have two presenters, about 20 minutes for each for doing the presentation, and then we have a section about 10 minutes for question and answers from audience. If you have any question, please write it in the chat, and then end of the presentation, we will ask the speaker your question. Yeah, thank you.
Thank you, Mehrshad. Thank you, Professor Gibson, for introduction. Today it's my pleasure to share our results on additive manufacturing of supermemory alloys, mainly on nickel titanium and nickel titanium niobium alloys. I'm Xiebin Wang from Shandong University, China. Before I start, I would like to introduce myself briefly. So I got my bachelor and master degree here in Shandong University, and got my PhD work in Belgium, KU Leuven, in 2014. Afterwards, I did 1.5 year postdoc also in KU Leuven, and starting from November 2016, I started work in Shandong University. And my research focuses mainly on additive manufacturing of nickel titanium-based alloys, including binary nickel titanium alloy and ternary and quaternary alloys. And of course, recently, I did a little bit of work on aluminum and titanium alloys. Today, I would like to share our results on laser pulsed bed fusion, or LPBF, of nickel titanium binary alloys, and LPBF in situ alloying of nickel titanium niobium ternary alloys. Firstly, I would like to introduce briefly what is a supermemory alloy. As compared with the conventional alloys, for the supermemory alloys, it shows the unique supermemory effect and super elasticity. For supermemory effect, it means if you deform this material and then heat it up, so increase the temperature, the deformed crust will recover back to its original shape. If you look at the stress strain curve, so after during loading, the material is deformed. After unloading, no recovery. So the sample remain in deformed states. But if you increase the temperature for the red curve, and then it will recover to its original shape. It's called supermemory effect. And also it shows super elasticity. If you look at the video, it looks like this kind of alloy has show very good elasticity. Look at the curve, and then if you deform it, it shows a plateau. This is caused by stress-induced multi-site transformation, and during unloading, the multi-site transform back to oscillatory phase. And in the meantime, the shape of the material also recovered back to its original shape. So this is called superelasticity, mainly caused by the transformation between obstinate phase and multi-set phase. Due to the unique properties, the supermembrane alloys have been widely used in many fields. For example, the medical parts like stents and staples. But for the nickel titanium alloys, it can only use in temperature between like -20 degrees to 80 degrees, because the transformation temperature is in this range. Of course, there's other system for supermembrane alloys like iron-based and copper-based alloys. But for the iron-based alloys, the supermembrane effect and superelasticity is not that high. And for the copper-based alloys, normally you need single crystals. So this transformation temperature limits the use of nickel titanium alloys. In order to improve, to tailor the transformation behavior and to widen its application of this kind of binary nickel titanium alloys, people add ternary elements to modify its transformation behavior. For example, add iron in nickel titanium to lower the transformation temperature, adding niobium to widen the transformation hysteresis, and for adding copper to narrow the transformation hysteresis, and for adding hafnium to increase the transformation temperature. It's called high temperature supermembrane alloys. But for this kind of alloys, there's several challenges to make this kind of alloys. Mainly, so I could summary. I did a little bit summary, so there are mainly two challenges. So the first one is difficult to process. So, for example, if you want to make nickel titanium and niobium ternary alloys, so they have a very large difference in the melting point for titanium, nickel, and niobium. So during casting, it's not easy to get a homogeneous melt, and the microstructure is not homogeneous and will give you a lot of problems for utilize of this kind of material. And also, there's easy to oxidize, and also easy to form a lot of intermetallics. Even after you cast this kind of alloys, and when you want to make some devices, you will meet a lot of problems, mainly because of the difficult to machining this kind of materials and difficult to weld this kind of materials, especially during welding. There's a lot of cracks and defects. It is very harmful for the mechanical properties. And the second challenge is difficult to control the microstructure and the properties. It is well known that the transformation behavior of nickel titanium alloys is very sensitive to its composition. For example, for nickel-rich alloys, if you add 0.1% of nickel, and the transformation temperature will decrease around 20 degrees. And also, when you add ternary elements, the transformation temperatures will change a lot. It depends highly on the type of elements and the amount of the elements. And also, for the nickel titanium based alloys or other supermembrane alloys, we all suffer from the functional degradation. So in order to address these challenges, we want to use laser polymer fusion or additive manufacturing to solve all the problems. What we want to do is to use laser polymer fusion first as a manufacturing method to make geometrically complex nickel titanium ternary or even quaternary structures. And then we want to use laser polymer fusion as a metallurgical method to do in situ alloying to make the nickel titanium ternary alloys use like, for example, nickel titanium powders and niobium powders to make nickel titanium niobium ternary alloys. And also we want to use laser polymer fusion to tailor its microstructure and transformation behavior, and of course the functional properties. So because the microstructure of or the transformation behavior of nickel titanium alloys is very sensitive to its microstructure, and if you change the LPBF process, you will more or less modify the microstructure, and then based on this relation, we could tailor or at least change the transformation and behavior of these alloys. I will show the examples later. And if we achieve all this, we may have the approaches to make complex nickel titanium based alloys or nickel titanium based structures with tailorable properties. In order to achieve this, firstly, we analyze the interaction between laser and nickel titanium powders. And we found that a lot of phenomena will occur during this process. For example, nickel evaporation, because nickel has a lower melting point than titanium. So at high temperatures, nickel is more easy to evaporate as compared with titanium. After process, the additive manufacturing, the parts will have a lower content as the powders. And of course, there will oxidation of titanium elements and precipitation of nickel 4 titanium 3 particles or titanium 2 nickel particles and also other particles. And of course, for additive manufactured parts, they show strong texture, high density of dislocations, and high residue stresses. And of course, you will get cross grains and microstructure inhomogeneity. And for all these factors, we found that the first one is the most important factor that influencing the transformation behavior and the functional properties of nickel titanium alloys. And then we printed these samples and did a process optimization. And it's very similar with other alloys. For example, with a high energy input, you got a lot of keyhole pulls, and the low energy input, you get a lot of lacquer defects. But there's a large process window to get this dense and almost defect-free samples. And then we checked the phase transformation behavior. It's quite interesting that if you look at the transformation peaks, it's so the transformation peaks shift gradually to the lower temperature side if you increase the scanning speed. Of course, you keep the laser power, hatch spacing, and the layer thickness constant. Only change the scanning speed. So the transformation temperature decreases with the increase of scanning speed. And of course, it also decreases with the increase of the high spacing. So it means that if you decrease the energy input, the transformation temperature decreases. So the mechanism and the underneath this phenomena is quite clear, because if you lower the energy input, you lower the nickel loss by evaporation. So lower nickel evaporation leads to a higher nickel content in the matrix, and then lower Martin-Size transformation temperature. So the very important aspect of this results is that if you wanted to tailor the transformation temperature, you have to control the nickel content very precisely, like 0.0%. But with LPBF, you can just change the scanning speed. It's very easy to modify the scanning speed, and then to tailor the transformation temperatures. And if you want to tailor transformation temperature, you have to modify the process parameters. But if we learn from the LPBF of other alloys, normally you need optimized process parameters to get a fully dense material. But here we change the scanning speed from 400 millimeter per second to 1,200 millimeter seconds. Of course, there will cause a lot of defects in this material with a high energy input, like 400 millimeter per second sample. But interestingly, if we change this kind of if we change this scanning speed from 400 to 100,000 millimeter seconds, the ductility or the total elongation of these samples is almost the same, all higher than 12%. It means that even we have such a lot of large keyhole pores, it doesn't undermine the ductility of this material. So it's quite different with other alloys like aluminum and titanium alloys. But the reason for this phenomenon is very simple. If you look at this stress strain curve, there's a plateau at a very low stress level, below 200 megapascal, or even at 100 megapascal. So, and such low stress level, and the sample can deform like 6%. So it means at a very low stress level, and the sample shows a plateau, and at this plateau, the pores doesn't break, and then it gives you a high ductility. And then we check the functional properties of this binary alloy. It shows very good shape memory effect at a free recovery, and of course it shows also good shape memory effect at a constant stress of 100 megapascal. And we also checked this recovery force of this printed sample. The highest recovery force is higher than 450 megapascal. And also we measured the superelasticity of this printed binary alloy with the pre-strain of 5%. It can bear, can survive higher than 150 superelastic circles. And of course, after 150 circles, the sample, the residue strain is lower than 1%. So it means this kind of materials show very good superelasticity elasticity, and it's comparable to the conventional made nickel titanium alloys. And then so the previous study shows that if you change the LPBF process parameters, you will change the transformation temperatures of nickel titanium alloys. Then we selected 2 parameters and to produce this kind of layer structured material, and each layer has 200 micron. And so different layers have different transformation temperature, and then at room temperature we got this layer structured microstructure. For the colored parts, it's martensite, it's austenitic phase, and for the black parts, it's black layer is martensite phase, because martensite has very fine less, and for EBSD it's not easy. It's not possible to get clear KQG patterns. Then at room temperature, we got it's the austenite and martensite layered microstructure. And for these materials, we could widen its transformation interval. For example, for the conventional nickel titanium alloys, the temperature range between martensite transformation start temperature and finish temperature is around 20 to 40 degrees. But this material shows a very wide transformation interval of 130 degrees. And with such wide transformation interval, it gives you a lot of interesting phenomena like Elyas effect. For this layer structured materials, the elastic modulus is almost constant with a change of temperature between 250 degrees and 370 degrees. And for the road, for the conventional made the nickel titanium alloys, the elastic modulus decreases with increase of with decrease of the temperature. And also it shows a very high damping properties over a wide temperature range. For the blue curves and for the red curves, it's road nickel titanium plates. And based on the experience on making nickel titanium parts by LPBF, we continue this work to use LPBF as the in situ alloying method to make nickel titanium niobium ternary alloys. Before we started the experiments, we did some more calculations to see whether we after adding niobium elements, if there's a lot of solidification cracks. And we did some calculation with using small calc software, and the results showed, so for this red curve, the results show that if you add 1% or 3% niobium, there will be a lot of solidification cracks. But if you add higher niobium, like 7 and 9%, and there may you will get a crack-free sample. And then based on this analysis, we did the experiment parts. We use nickel titanium powders. This is a pre-alloyed powders with nickel content of 50.6%. And we use niobium elemental powders, and they have the same, almost the same size as nickel titanium powders. And after mixing, it looks very homogeneous. And we checked the particle size distribution of these particles and X-ray of nickel titanium and niobium powders. And of course, the transformation behavior. So after adding niobium, the transformation temperature doesn't change because niobium doesn't transform at temperature between minus 150 and plus 150 degrees. And then we did the process optimization And we change, this time we change the laser power, and at the low energy input, there's a lot of unmelted niobium particles. So the blue dots is niobium particles. And at a higher energy input, there's a lot of keyhole pulse. So for the sample printed with 200 watts and 240 watts, there's less keyhole pulse and less unmelted pulse. So we selected the 200 watts to print all the nickel, titanium, niobium samples. And of course, as expected for the sample with 1% and 3% niobium, there's a solidification cracks, this red lines. Here is cracks. And then we check the microstructure, and it's a highly inhomogeneous microstructure, and there's unmelted pores, but for unmelted niobium pores, there's a strong metallic bonds with matrix, because there's a eutectic region between unmelted niobium particles and the nicotinium matrix. And also there's a lot of nickel-rich spherules, and this nickel-rich region, there's niobium dendrites and cellular structures. Of course, if you look at more details with TM, there's also some niobium rich precipitates, and we checked the chemical composition, and it's not a pure niobium, it's niobium with some titanium. It's beta niobium particles. And then we check the transformation temperature of this alloys. This result is actually very interesting. We know that for the binary alloys, if you increase the energy input, you will increase the transformation temperature. For example, here, if you decrease the laser power or increase the laser power, the transformation temperature will increase from the black curve to the blue curve. And of course, if you add only 1% niobium, show similar trends as binary alloys. But if you add the 3% niobium, the transformation, except for the sample printed very low energy input, energy density, the blue curve and the red curve. So the rest of the samples show very similar transformation temperatures. So it means the transformation behavior is not that sensitive to the laser power change. And then if you increase the niobium addition to 5%, the transformation temperature actually increase with decrease of the laser power, or increase with a decrease of the energy input. It's totally opposite as observed in nickel titanium or one niobium alloys. So it means of course for the non-niobium samples, it shows a similar trend. So decrease of laser power, increase of transformation temperature. So if you look at the last figure, it's clear, it shows that for the low niobium addition samples, transformation temperature increase with laser power, and high niobium content samples, the transformation decrease. That means a reversal of the effect of laser power on martensite transformation temperature occurs with the increase of the niobium content. And what, why it happens, and what is the mechanism behind this phenomenon? Actually, this story is quite simple. It's a competition between the factors that increase the temperature and the factor that suppress multi-site transformation. So the factor that increase the transformation temperature with increase of the energy density is mainly nickel evaporation. So more nickel evaporation, more higher multi-site temperature transformation temperatures. But there's also factors that suppress multi-site transformation. For example, the dissolved niobium atoms in the matrix will cause severe lattice distortion, and this kind of lattice distortion will suppress multi-site transformation, and this kind of effect will increase with the increase of nickel addition. So with lower nickel with lower niobium addition, the factors that increase transformation temperature is a key factor, and with higher nickel addition, with higher niobium addition, the factor that suppress multi-site transformation is a key factors. So the transformation temperature changes a lot with the increase of niobium addition. And for nickel titanium niobium ternary alloys, the most important properties is the transformation history. So it means the difference between the cooling peak and the heating peak. So for the printed alloys, so normally we check the not only for the printed alloys but also for the conventional alloys. We check the hysteresis. Firstly, do a pre-deformation and then heat it up to check the transformation temperature. Because, for example, if you look at this, the first curve, the first figure. So without a
Xiebin, sorry for interrupting. I just want to say we almost use more than enough time for the first presentation. I appreciate if you wrap up your part and to go to the questions. Thank you.
Okay, I will quickly finish this presentation. Okay. So with this with high with addition of niobium, we can wide its thermal hysteresis similar to the conventional nickel-titanium niobium alloys, and we checked the Xiebin memory effect. It's so good a Xiebin memory effect, and but its ductility is not that good. So we do heat treatment to increase its ductility. And after solution treatment, we could increase the ductility to over 12%. But after solution, sorry, it's we compared the mechanical property with other alloys, and it's good as compared with the additive manufactured parts, but it's lower than the wrought parts. After solution treatment, the transformation temperature increases to a high value, and this is not what we want for nickel-titanium niobium ternary alloys. Then we continue this work by using a high nickel pre-alloyed powders, and of course we add extra nickel to lower the transformation temperature. After solution treatment, all these samples show very good ductility. And well, we could suppress martensite to like 187 Kelvin. It's very low, and it's comparable to the conventional nickel-titanium niobium ternary alloys. And then we checked the transformation hysteresis is so large and comparable to the conventional alloys. And we checked the Xiebin memory effect. So good Xiebin memory effect and could be used for couplings. And also we checked the recovery stress with a change of temperature, and it's also show very good results. And this is the conclusions, and this is related to publications.
Okay,
That's
thank you, Xiebin. Thank you for the presentation. We enjoyed very much. Sorry for the limited time. I'm sure you could share more than 20 minutes or 30 minutes, but yeah, we move to the second part about the question from the audience. I see already they share their question here. I try to be quick as much as possible. Also for this part, the first audience asks you thermomechanical response of shape memory alloys always being come from deformation and thermal treatment. A logical question is that how homogeneous properties you can get in this alloy by additive manufacturing process.
for this question, actually after solution treatment for the binary alloys, it's not a problem. You get a very homogeneous materials. But for the in situ alloy, like what we did, nickel, titanium, niobium, it's not easy to get a homogeneous structure. But if you use pre-alloyed powders, that's not a problem. So if you always use the pre-alloyed powders, you will get very homogeneous microstructure.
Okay, thank you. The other question we have here is any medical application the fatigue performance is very important for medical application. What is your view about the additively manufactured SMAs and its fatigue properties?
Well, it's a very good question, but actually for the medical implants, it doesn't need very large deformation, and this conditions, the additive manufactured parts could meet the requirement of the standards. We did a lot of fatigue tests, and it's no problem, and to pass the ASTM standards. So it shows good superelasticity. It shows good fatigue properties, but don't deform a lot.
Okay, very good.
So there's an example. We did a lattice structure of a kit of nickel-titanium alloys, and it passed 5 million circles. It's no problem.
Okay. Just one short question. The question or more, I ask people if you want to have asked question, please feel free to contact Xiebin later. One quick question in the end is what kind of LPPF setup you use for 3D printing of these alloy, NITI and NITI Novium?
Sorry, what is the
The exact question is what kind of SLM or LPBF machine did you use for printing the alloy you presented in this presentation?
We use Renishaw
Okay.
machine. It's Renishaw 500E.
Okay. All right. Thank you. Thank you very much. Sorry I couldn't go to all the question in the chat. Apologize for that. And thank you, Xiebin, for your presentation. We enjoyed very much. I move to second speaker, Professor Ghafoori from University of Hannover. I see 15 minutes left. Sorry, Elyas, for that, but we listen to you. Please share your presentation with us.
Thank you very much, Mehrshad. You hear me well, right?
Yeah, we hear you, see you, and now we can see also your screen.
Very good. So you see the screen with the presentation,
yes.
Right? Okay. Good. Yes, so my name is Elyas Ghafoori. I try to make it a bit faster so that we almost finish at the same time as expected. I'm the professor of steel, composite, and lightweight structures at Leibniz University of Hannover. I moved to this university nearly 1 year ago, and before that I used to work at EMPA, Swiss Federal Laboratories for Material Science and Technology in Switzerland, also at ETH Zurich. So the research I'm presenting here today, it's mainly about the research we have done at EMPA. So all the credits go to this institute. My colleagues there are intensively working, and also credits go to these authors and co-authors listed here for the work that have been done by the PhD and master student. I'm talking today about memory steel for smart steel construction structures, and mainly it is a review on recent development and applications on this topic. So unlike the last speaker, it's not mainly about AM of shape memory alloys, rather than a new type of shape memory alloy, iron-based shape memory alloy, that provides a good potential for larger scale application in construction in civil engineering domain. So just a short overview about our activities in the Institute for Steel Construction. I try to turn on my laser. Yes, we are working on different fronts. So advanced structural materials, which includes shape memory alloy, for example, but also fiber reinforced polymers, CFRP, or glass fiber reinforced polymer, GFRP, are one of those. Epoxy adhesives, but also additive manufactured steel using powder bed fusion, but also wire and arc additive manufacturing. This could be a steel, but also shape memory alloys. Automated robotic construction, robotic welding, different type of AM processes, a 3D printing of shape memory alloy, which we call then 4D printing. Still support a structure, so we are growing with the scale. So here at the smallest scale, and here it's becoming a bit larger scale with wind turbines. In particular, the support structure of wind turbines, which are mainly 70–80% steel. We are working on different details: grouted connection, welded connection, bolted connection, and also their structural health monitoring. And of course, we are also working intensively on simulation. So here it shows simulation of wire and arc additive manufacturing of on an existing steel plate. Our goal, however, is to use these techniques for sustainability reason to reach net zero 2050 in construction. Today, I'm talking, so you see that there are a wide spectrum of activities. I mainly talk about advanced structural materials, shape memory alloys in particular. The last speaker has given you a good overview about shape memory alloy. I keep it short. This is superelasticity. That means an energy dissipation, and everything happens at room temperature. And this is shape memory effect. That means that we pre-strain this the shape memory alloy, and then after preheating, after heating here with hot water and here with temperature, they can actually recover their shape. So during the pre-straining, the material is changing from austenite to martensite phases, and during activation they change from martensite to austenite. So the last speaker talked about mainly superelastic behavior, and now I'm talking about shape memory effect. So it's actually then complementary, right? There are different SMA systems. There are nickel-based systems, nickel titanium, copper, and so on, and copper-based also alloys. There are different systems. Also iron-based, they have different systems. Fe, nickel, cobalt, titanium, which is also used, which is work also by our colleagues in our in Kassel University. But today I'm talking about Fe magnesium manganese silicium. So that's a special alloy that has been developed and patented at Mehrpouya about 15-20 years ago. Why this alloy has been engineered and developed for civil engineering applications. Why that is important? Because the alloy has high Young modulus. So it has a when we talk about nitinol, the Young modulus is relatively is good, but it's about 30 to 70. With iron-based gigapascal, and here with iron-based shape memory alloy, we can go up to 200 gigapascal. So it's actually good. It's in the order of steel. So you can really use it as a structural member. Also, it's very cheap. With nitinol, some sort of nitinols, they're expensive and sometimes as expensive as gold. With iron-based shape memory alloy, patented, developed here, we go relatively the same price scale as stainless steel. So it's still more expensive than structural steel, but it's not as expensive as gold. And also the transformation temperature for a feasible recovery stress has been set to those that are feasible for construction. In construction, normally we deal with temperatures that are between -30 to plus 70 or 80. This is the exact composition you see here. From 2018, there is a company called Refer that is producing this alloy commercially, and that's the only shape memory alloy that has been commercialized so far. So you can see that here is the production line for rib bars. So here, such a ripped bar you often see in construction as steel, and they put that in concrete. And when the concrete is casted, just by applying electricity on either side of the bar, you can activate the shape memory effect, and then the rebar pre-stress itself. You can see the rebar here, but also we have strips. So today I mainly talk about the strips, but they are the same. They have the same kinds of behavior. How do we use them? So you can see here a stress strain diagram and also a stress temperature diagram. My talk today is actually a bit about the application of shape memory alloy. We of course also work a lot on characterization, optimization, and improvement of shape memory effect, but also superelasticity. As the last speaker correctly mentioned, iron-based shape memory alloy, they have limited superelasticity, but they have very good shape memory effect. We tried recently within an EU project to improve the superelasticity of iron-based shape memory alloy by applying some special heat treatments. But also there are iron-based shape memory alloy systems that are they have a good superelastic behavior. Here I'm focusing on structural application, in particular with shape memory effects. So here we have stress strain and a stress temperature behavior. This diagram, this curve shows the pre-straining process and unloading. So we pre-strain let's say a strip, we unload that, right? And then we apply that to a civil structure. It could be a concrete beam, a steel beam, timber beam, and we could bond the shape memory alloy to a steel beam, or we could actually use rivets or bolt to connect them, and then we hit them and cooling down process. So during the heating process, you can see the stress increases, and you can see also the stress temperature diagram. We gain some stress during heating, but some stress during also cooling process. And with that, we can actually have our structure pre-stressed. So I don't know if you see the voice, but yes, here is the application, the first application of this type of iron-based shape memory alloy worldwide for strengthening of bridges. So this is a 113 years old bridge, bridge in Czech Republic that we strengthened with a few plates of iron-based shape memory alloy. So you can see on the top left picture the connection to steel structure, because the whole bridge is steel. They have a good compatibility. And then you can see here the activation blanket. So we activated with blanket. You can see on the bottom here is the truck test before and after strengthening. We have also, you see that here the connection is with rivets. We are actually working in civil engineering domain, so we try to find methods to use this innovative material in construction, and also how to apply them. So there we use mechanical anchors, and here we use adhesively bonded joints. So there are two ways of applying adhesively bonded joints: by partly bonding at the very end, or by fully bonding along the whole surface. You can see the shape memory. This is the strip with Sika adhesive, and here is the activation process. You see here we put some ice pack to keep the anchors cool, and then using the thermocouple, measure the temperature to make sure that we have the right temperature for activation. And of course, afterward, we did fatigue tests, more than 2 million cycle and a few beams, not only one beam, to make sure about the structural integrity of the system. So this is one application. I'm showing you also the applications. Here we have relatively young bridge. We design normally in civil engineering bridges up to 100 years, but this bridge near Zurich has more than 30 cracks in different part, small crack in complex detail, and there is no way actually to stop those cracks. This is a railway bridge, and these cracks grow until they are in a critical size, and then there will be failure of the part, not the whole bridge, of course. But if there are many cracks, then it's becoming critical. Here we actually try to use FESMA patch that could arrest the existing crack. We bond the FESMA to existing crack detail, and then we just hit the area over the crack to activate the pre-stressing, or to pre-stress the patch, and the reaction is applied to the crack. And when the crack is under compression, the crack will not grow anymore. We know that the crack is growing over under tension. So this is a running project right now. We have a few different PhD students. You can see also some of our publications here that they are trying with different type of patches, small patches as small as your palm, as your hand palm. So you can apply really quickly on the area where there is a crack, let it cure, and then hit it with different methods, whatever method is more convenient. We could actually apply also CFRP, carbon fiber reinforced polymer sheets, on top of that. There are different techniques we are trying right now, and by that we can of course decrease the amplitude of the stress along the steel plate, but also we can push the stress history from tangent at the critical detail near the crack. Under this patch, there is a crack to tension tension compression. So in that case, only the tension part is effective, from 0 to maximum tension, and not so we can reduce the stress amplitude. We did test, and we showed that by having such system, we can arrest existing crack. Of course, the bond is very important here. So we have done extensive tests on lap shear tests. So when this is a steel plate and this is a SMA plate, we bond that and we pull the SMA on the right side. And then we see how is the behavior of how is the debonding is propagating between shape memory alloy and between a steel plate. And from that, we can, of course, with different type of adhesives. Here you can see Sicador 30, but also Sica Power, but also Araldite. Any of them, they show different type of structural behavior. And then we drive bond slip behavior. Due to time, I will skip this, but I will come to this slide about 4D printing. So I showed you a few different, first of all, the process of manufacturing of the alloy I showed you here earlier. It's by so there will be it from the billets. There is a process, hot rolling process, typical hot rolling process. So the advantage of this alloy is that typical steel, let's say stainless steel manufacturing process can be used for production of this alloy. That's why it makes it suitable for larger scale manufacturing, and that's why the price is decreased. So you can actually use many existing production facilities that are in different countries existing for manufacturing of stainless steel for production of this alloy. And so there are billets, and those billets, there are hot rolling process, typical hot rolling process that we have these beams, girders, all the steel girders you see around you. Normally they are hot rolled up to 3 millimeter thickness of the strip. And then from 3 millimeter to 1.5 millimeter strip thickness, we go with cold rolling process. And cold rolling process is also a typical process. That's why the reason the alloy is cheap is that you can use traditional steel manufacturing process. You don't need a special equipment, furnace, and so on. And it doesn't have to be done under vacuum. That's very important. You can do it at atmospheric condition. And here we tried also 3D printing, not only with laser powder bed fusion. Of course, this part is actually done by our colleagues, the group of Dr. Christian Leinenbach at EMPA. He has his laboratory dedicated to additive manufacturing of shape memory alloy. We are mainly like the yes, we have collaboration with him, and yes, here we have done it with laser powder bed fusion, but also we have done wire and arc additive manufacturing of shape memory alloy. How do they work? Here we designed these 2.5D lattices. We designed this lattice in a way, or our PhD student, Mr. Jafar Abadi, has designed the lattice in a way that they show monostability. So when we push it down, the whole beam stays in elastic region. It doesn't. We do not overload the beam, and when we remove the load, they snap back. This is the and if you have one, you can actually put these cells on top of each other, and you can come up with a network of those. You can see that these beams are repeating everywhere. We can see nicely that during the loading process, we have negative stiffness here. We have force thresholding. And now that the load is removed, we see nicely, as I said, this FESMA doesn't have much of superelasticity, but we can design smart, complex details that gives system superelasticity. We don't say superelasticity anymore. We should say recentering. Not only recentering we can engineer, but we can engineer also force thresholding. That means here it is 400 Newton. If you have a valuable structure and you don't want to overload that valuable structure, you can design this in a way that you can get. So at the end, you saw also a bit of remaining deformation. By activation, you can also bring that to 0. Where do they where can this be used? They can be used, for example, in landing gears of airplanes, car bumpers, for seismic application in civil engineering, and as vibration and vibration mitigation in wind turbines or anywhere needed. Take home message: memory steel. We call it memory steel, but you can say iron-based shape memory alloy is a smart steel. When you say shape memory alloy, many people might not know what it means. But when you say smart steel, it's easier for people to understand. It's an alloy which has been designed and also used in civil engineering. It's the only one that is commercially available in construction. You can buy it actually. It has a strong shape memory effect that gives us the possibility for pre-stressing the structure. It has limited superelasticity. We are working to improve that. And unlike nickel titanium, which the last speaker also correctly mentioned, which is very sensitive in 3D printing, because during 3D printing, some of the elements are gone, evaporated, and then that affects substantially the behavior of shape memory alloy, nickel titanium in particular. And here, this alloy is not very much sensitive to a bit of more or less manganese or chrome. So it has a good stability for 3D printing application. So it's not very sensitive to the exact components and ingredients. Thank you very much for your attention. If you are interested to know more about shape memory alloy, you can scan our LinkedIn and webpage of our institute. If there is any question, I will be happy to answer.
Okay, thank you, Elyas. Thank you very much for your presentation. We already have a couple of questions here in the chat. I start with the one I see. We found FESMA very brittle when we produce with LPPF. How did you overcome this?
Different process might have different result. We actually do some heat treatment often on those FESMA. Depends how you do that, of course, but if it is a brittlity, we didn't have this issue that they are brittle. Even as printed, they were good. So what I showed you, they were as printed, but to improve further ductility, you can use, you can do some sort of heat treatments. For this particular FESMA, we have actually a few papers that they are dealing with how to heat treat additive manufactured iron-based shape memory alloy to improve the ductility. I will be happy to share it with you. You can just send me an email, please. My email, yeah, if you go to our website, you will see my email. Yeah.
Okay. The other question, thank you for presentation concerning possible application in civil engineering. I would like to know whether possible long-term effects such as stress relaxation or compound problem were also investigated in your studies.
Yeah. I personally did also high cycle fatigue test on the same. So this is a new structural material. any new structural material, they have to go through very hard certification process. Fatigue, creep, relaxation, corrosion, galvanic. We have different type of corrosion: galvanic corrosion, stress, also normal corrosion, stress corrosion. We have done research nearly on all of them. In our fatigue test that I actually did myself, we have 2 papers on fatigue of iron-based shaped member alloy. There are relaxation. To take them into account, we consider 15, depending on the stress amplitude, we consider 15% less pre-stressing in our design. So if pre-stressing here, we get about 350 to 450 when we activate with a temperature of 200 Celsius, sorry. If we get 400, we don't design it for 400, we design for a bit less, 380, to take into account future reduction of the pre-stressing.
Okay, thank you. Thank you, Elyas. I'm sorry I cannot go through all questions. I would suggest you to send an email to Elyas if you have more questions or would like to know more about his research. I would like to thank you all for participation in this webinar. It was the first one. We just started. We are going to have more, ideally every 2 months, let's say. And if you would like to know more about the next meeting, I would suggest you to follow the LinkedIn page of the webinar with the same name. It is AM Smart. And thank you for your time and hopefully to see you next time. And I would like to thank you all the speakers, Elyas and Xiebin, and also Ian for being in this meeting and webinar. Thank you all.
Thank you, Mehrshad, to arrange the whole meeting.
Okay, thank you. Bye.